The ugly truth about Saturn's rings. When you think of Saturn, you think of those magnificent rings, those spectacular bands of ice and rock that make it the jewel of our solar system, those iconic features that have captivated humanity for over 4 centuries. But there's an ugly truth lurking behind all that beauty, and it's something that most people don't know. Saturn's rings are dying. They're disappearing right before our eyes, vanishing into the planet itself at a rate that should terrify anyone who appreciates the cosmos. And the worst part, they might be far younger than we ever imagined, meaning humanity may have emerged at precisely the right cosmic moment to witness them. Let me explain why everything you thought you knew about Saturn's rings is probably wrong, and why the reality is far more dramatic, violent, and temporary than anyone expected. The discovery, when humanity first saw the impossible. The year was 1610. Galileo Galilei, the Italian astronomer who would revolutionize our understanding of the cosmos, turned his primitive telescope towards Saturn for the first time. What he saw confused him so thoroughly that he spent years trying to understand it. Through his crude 20-power telescope, Saturn appeared as 3 bodies touching each other. He wrote to the Duke of Tuscany, describing the planet as a composite of 3 objects that almost touched one another and never moved relative to each other. The middle object was about 3 times the size of the lateral ones. Galileo thought he had discovered 2 massive moons on either side of Saturn, or perhaps strange handles attached to the planet itself. 2 years later, in 1612, Galileo turned his telescope back towards Saturn, expecting to see those same companions. Instead, they had vanished completely. The planet appeared as a single, solitary sphere. Galileo was mystified. He wrote in desperation, questioning what could have happened to these objects. He even referenced the Greek myth of Saturn devouring his children, wondering if somehow the planet had swallowed the objects he had seen before. This disappearance haunted him. How could something so substantial simply cease to exist? By 1616, Galileo observed Saturn again, and the companions had returned. But now they appeared different, more like arms or handles extending from the planet. Galileo concluded that Saturn must have some kind of appendages, though he could never quite figure out their true nature. His telescope simply wasn't powerful enough to resolve the fine details. For 43 years, this remained the understanding of Saturn among astronomers. It was a planet with mysterious handles or ears, objects that appeared and disappeared in baffling cycles. The breakthrough came in 1655, when Dutch astronomer Christiaan Huygens began grinding lenses with his father. Using a 43-power refracting telescope of his own design, Huygens observed Saturn with far greater clarity than Galileo had achieved. After careful study, he concluded that Saturn was surrounded by a thin, flat ring that nowhere touched the planet's body and was inclined to the ecliptic. This was a radical proposal, a detached ring surrounding a planet. Nothing like it had ever been conceived in the history of astronomy. Huygens was so protective of his discovery that he initially published it as an anagram, a string of seemingly random letters that could be unscrambled to reveal his finding. 3 years later, in 1659, he published his ring hypothesis in Systema Saturnium, forever changing our understanding of the solar system. But even Huygens's discovery was incomplete. He believed the ring was a single solid disk. It took Giovanni Domenico Cassini, the Italian-born French astronomer, to discover in 1675 that there was a large gap within the rings. This gap, now known as the Cassini division in his honor, proved that the rings couldn't be a single solid structure. The rings were more complex than anyone had imagined. As telescopes improved through the centuries, astronomers discovered more and more structure within Saturn's rings. In 1850, William Cranch Bond and his son George Phillips Bond discovered the C-ring. In 1933, Nikolai Barabashev and Boris Semikhin identified the faint D-ring. Walter Fableman discovered the E-ring in 1967. When NASA's Pioneer 11 spacecraft flew by Saturn in 1979, it discovered the F-ring. Voyager 1 found the G-ring in 1980. Each discovery revealed that Saturn's ring system was far more intricate and complex than the simple disk Huygens had described. The mystery of why Galileo's companions had disappeared and reappeared was eventually solved. Saturn's rings are incredibly thin compared to their vast diameter. While they span more than 270,000 kilometers across, they're only about 10 to 30 meters thick in most places. When viewed edge-on, as happens every 13 to 16 years from Earth's perspective, the rings essentially vanish from sight. Galileo had accidentally observed a ring plane crossing, witnessing the rings edge-on when they reflected virtually no light back to Earth. This explained the appearance and disappearance of Saturn's companions. They had never gone anywhere. Humanity simply couldn't see them when they were turned sideways. The composition, a frozen wonderland built on violence. Now that we understand how humanity discovered Saturn's rings, we need to understand what they're actually made of. The answer surprised scientists when they finally determined the composition through spectroscopic analysis and spacecraft observations. Saturn's rings are almost entirely water ice. We're talking about 99.9% pure water ice with only trace amounts of rocky material mixed in. Think about that for a moment. The most spectacular ring system in our entire solar system, visible even through amateur telescopes from Earth, is essentially frozen water floating in orbit around a gas giant. The particles that make up these rings vary dramatically in size. On the small end, you have particles no bigger than dust grains, measuring just micrometers across. On the large end, you have chunks the size of houses, boulders, even mountains. Some particles measure 10 meters or more in diameter. Billions upon billions of these icy particles orbit Saturn in a vast, flat disk. The Cassini spacecraft was able to directly measure the total mass of the ring system during its final orbits in 2017, when it passed between the planet and the innermost rings. The measurement revealed a mass of approximately 1.54 times 10 to the 19th kilograms, which is about 0.41 times the mass of Saturn's moon Mimas. To put that in perspective, it's roughly equivalent to two-thirds the mass of Earth's entire Antarctic ice sheet, spread across a surface area 80 times larger than our planet. The rings are organized into several distinct sections, named alphabetically in the order of their discovery rather than their position from Saturn. The main ring system consists of the C ring, B ring, and a ring, working outward from the planet. These are the bright, dense rings that are easily visible even through small telescopes. The C ring is the innermost of the main rings, starting about 74,000 kilometers from Saturn's center. It's somewhat translucent compared to the B ring, which is the brightest and most massive of all the rings. The B ring contains the highest concentration of material and creates the most dramatic visual impact. Beyond the B ring lies the Cassini division, that gap Cassini discovered in the 17th century. It spans about 4,800 kilometers and appears dark from Earth, though Voyager discovered it actually contains fainter ringlets rather than being completely empty. Past the Cassini division lies the ring, another bright and prominent ring. Within the ring, there are two notable gaps. The Encke gap, about 325 kilometers wide, is cleared and maintained by a small moon named Pan that orbits within it. The Keeler gap, much narrower at only 35 kilometers wide, is maintained by an even smaller moon named Daphnis. These gaps aren't truly empty. They contain some ring material, but the gravitational influence of these small moons prevents particles from accumulating there permanently. Beyond the main rings lie several fainter, more diffuse rings. The D ring is extremely faint and lies closest to Saturn, inside the C ring. The F ring, discovered by Pioneer 11 in 1979, is narrow and complex, displaying braided and kinked structures unlike anything else in the ring system. This ring is shepherded by two small moons, Prometheus and Pandora, which orbit just inside and outside the ring, using their gravity to confine the ring particles between them. The G ring and E ring are even more tenuous. The E ring is particularly notable because it's enormous, extending from the orbit of Mimas all the way out to Titan's orbit, spanning roughly 1 million kilometers. Cassini discovered that the E ring is continuously replenished by ice particles ejected from geysers on Saturn's moon Enceladus, making it one of the few rings with a confirmed ongoing source of material. The temperature of the rings varies depending on their location and the angle of sunlight hitting them. During Cassini's observations, temperatures in the ring were measured as low as -230 degrees Celsius when sunlight hit them edge-on during Saturn's equinox. The rings' high reflectivity, their albedo, indicates they're made of relatively pure ice. If they were contaminated with significant amounts of dark material like rock or organic compounds, they would appear much darker. This purity raised immediate questions. If the rings had been around for billions of years, constantly bombarded by meteoroids from interplanetary space, they should be much dirtier. This observation became one of the first hints that something about our understanding of the rings' age was fundamentally wrong. The rings show tremendous structure on all scales. There aren't just a few broad rings with occasional gaps. High-resolution images from Voyager and Cassini revealed that the rings contain hundreds of thousands of individual ringlets, separated by narrow gaps. Density waves ripple through the rings, created by gravitational resonances with Saturn's many moons. These waves look like grooves in a cosmic record, spiraling outward from points where ring particles orbit at specific ratios to the orbital periods of moons. The physics describing these density waves is the same physics that describes the spiral arms of galaxies. Saturn's rings, in effect, are a miniature galaxy of ice and rock, following the same gravitational choreography that shapes structures throughout the universe. The age mystery, everything we thought was wrong. For decades, scientists operated under a reasonable assumption. Saturn formed about 4.5 billion years ago during the early days of our solar system. The rings, most researchers believed, formed around the same time, either from leftover material from Saturn's formation or from the early destruction of a moon. This would make the rings primordial, as old as Saturn itself, ancient features that had existed throughout nearly the entire history of the solar system. This belief made intuitive sense. The rings are massive, they're stable, they orbit within Saturn's Roche limit, the region where tidal forces are strong enough to tear apart any large body. They seemed like permanent fixtures of the Saturnian system. But there was always a nagging problem. The rings are too bright. They're too clean, too pure. If you left water ice exposed to space for 4.5 billion years, constantly bombarded by micrometeorites, dust, and debris from interplanetary space, that ice would become contaminated. It would darken. The rings should be covered in a layer of accumulated rocky material, lowering their reflectivity substantially. Some scientists proposed that the rings might be continuously cleaned somehow, perhaps by impacts ejecting the darkest material or by processes that preferentially removed rock while retaining ice. But these explanations always felt like special pleading, adding complexity to avoid an uncomfortable conclusion. The Cassini mission, which orbited Saturn from 2004 to 2017, was designed to answer fundamental questions about Saturn, its rings, and its moons. During its final year, Cassini performed a series of daring maneuvers called the Grand Finale. The spacecraft executed 22 orbits that passed between Saturn's cloud tops and the innermost edge of the rings, diving through a region no spacecraft had ever explored. These orbits were dangerous. Even tiny particles at orbital velocities could damage or destroy the spacecraft. But they were also scientifically invaluable because they allowed Cassini to measure Saturn's gravitational field with unprecedented precision. Why does measuring gravity matter for understanding the rings? Because gravity reveals mass. By tracking how Cassini's trajectory changed as it flew near Saturn and its rings, scientists could separate the gravitational pull from the planet itself and the gravitational pull from the rings. This allowed them to calculate the rings' total mass with remarkable accuracy. The result shocked the scientific community. The rings contain far less material than expected. Based on that mass and modeling how rings evolve over time, researchers concluded that Saturn's rings likely formed within the last 10 million to 100 million years. Let me emphasize how young that is in cosmic terms. 100 million years ago, dinosaurs still walked Earth. The Cretaceous period was in full swing. T-Rex was hunting. Triceratops was grazing. Flowering plants were spreading across the continents. If Saturn's rings formed at the younger end of that estimate 10 million years ago, humans and our chimpanzee relatives hadn't even diverged yet. The entire human lineage emerged in a solar system where Saturn already had its magnificent rings, but barely. The rings, it appears, are cosmically recent additions to Saturn, not ancient features at all. This discovery sent shockwaves through planetary science. It raised immediate questions. If the rings are that young, where did they come from? What catastrophic event created them so recently in solar system history? Why does Saturn have such spectacular rings when Jupiter, Uranus, and Neptune have only faint, sparse ring systems? And most troubling of all, if the rings are that young and Saturn is losing ring material continuously, as Cassini discovered, then the rings are temporary. They're a transient phenomenon. They won't last forever. It's worth noting that not all planetary scientists fully agree on the young age interpretation. Some researchers have proposed that the rings could be ancient but somehow recycled or cleaned, keeping them bright despite their age. However, the weight of evidence from Cassini's measurements, particularly the low mass, high purity, and rapid loss rate of the rings, strongly favors the young age hypothesis. The majority of ring scientists now accept that Saturn's rings are likely less than a few 100 million years old. The low mass of the rings became the key piece of evidence supporting their young age. A massive ring system that formed billions of years ago would have evolved and spread over time, but it would still retain significant mass. A low-mass ring system, however, points toward recent formation. The rings haven't had time to accumulate contamination from billions of years of bombardment. They're bright because they're young. They're clean because they haven't been exposed to space weathering for eons. Based on the measured influx of dark micrometeoroid material and the current purity of the rings, scientists calculated that it would take only tens to hundreds of millions of years for the rings to reach their observed contamination levels, not billions of years. Some scientists pushed back against this conclusion. They proposed that perhaps the rings are ancient but have been recycled somehow. Maybe ice from Saturn's moons is continuously replenishing the rings, keeping them bright despite their age. Maybe the rings underwent some rejuvenation event that refreshed their composition. But Occam's razor suggests the simpler explanation. The rings are young because they are young. They formed relatively recently, and that's why they look relatively young. Formation, the violence that created beauty. If Saturn's rings are young, then something violent must have created them relatively recently in solar system history. Scientists have proposed several scenarios, each involving destruction on a massive scale. The leading hypothesis, supported by simulations published in 2023, involves the collision of two icy moons in orbit around Saturn. Here's how it might have happened. A few 100 million years ago, Saturn's satellite system looked different than it does today. Among Saturn's moons were two mid-sized icy bodies, perhaps each several hundred kilometers in diameter. For millions of years, they orbited peacefully, but orbital dynamics are never truly stable over long timescales. The gravitational influence of the Sun, despite being far away, can have cumulative effects on moon orbits through a process called resonance. When two bodies have orbital periods that are simple ratios of each other, like 2:1 or 3:2, they experience repeated gravitational tugs at the same point in their orbits. Over time, these small tugs add up, potentially destabilizing orbits that appeared stable. This is precisely what may have happened. Two of Saturn's moons drifted into a resonance configuration with each other. Their orbits became increasingly elliptical and tilted. Eventually, their paths crossed. The resulting collision occurred at immense velocity, perhaps several kilometers per second. The impact was catastrophic. Both moons shattered into countless pieces, ranging from mountain-sized chunks to microscopic dust particles. The debris scattered throughout the region around Saturn. Here's where the physics gets interesting. The collision occurred near Saturn's Roche limit, the distance from Saturn where tidal forces become stronger than a body's self-gravity. Inside the Roche limit, objects cannot hold themselves together. The differential gravitational pull between the near side and far side of an object exceeds the object's own gravity trying to hold its parts together. For an icy body like a moon, the Roche limit for Saturn is about 140,000 kilometers from the planet's center. Material scattered from the collision that fell inside this limit couldn't reaggregate into new moons. The tidal forces were too strong. Instead, the material spread out into a disk, forming rings. Simulations conducted by NASA researchers and their international partners show that a collision of this type naturally produces Saturn's ring system. The researchers ran nearly 200 different collision scenarios, varying the sizes of the moons, their compositions, the angle of impact, and the collision velocity. A wide range of these scenarios succeeded in producing rings similar to what we observe today. The simulations also explain why Saturn's rings are almost entirely water ice with very little rock. When two icy, differentiated moons collide, much of the rocky material from their cores would plunge directly into Saturn or be scattered to regions outside the Roche limit where it could form new moons. The icy mantles, however, would shatter into vast clouds of frozen fragments. This icy material, scattered within the Roche limit, would settle into the plane of Saturn's equator, forming the magnificent ring system we see today. An alternative scenario involves a single large moon rather than two colliding moons. In this version, called the chrysalis hypothesis, and proposed by researchers at MIT in 2022, Saturn once had an additional large moon, comparable in size to Iapetus, Saturn's third largest moon. This moon, nicknamed Chrysalis, orbited Saturn for billions of years. It played a crucial role in Saturn's dynamics, helping to maintain a gravitational resonance between Saturn's axial tilt and Neptune's orbit. But somewhere between 100 million and 200 million years ago, Chrysalis's orbit became unstable, possibly due to gravitational interactions with Titan and other moons. The moon spiraled inward, eventually grazing Saturn's Roche limit. Tidal forces tore it apart. Approximately 99% of the moon's mass plunged into Saturn, while the remaining 1% of icy outer layers scattered into orbit, forming the rings we see today. The scenario has some compelling aspects. It explains not just the rings, but also Saturn's unusual axial tilt. Saturn tilts at about 27 degrees relative to its orbital plane, significantly more than expected for a planet of its size that formed in a relatively flat protoplanetary disk. The chrysalis hypothesis suggests that for billions of years, Saturn's tilt was maintained by a gravitational resonance with Neptune, but this resonance required the additional mass and angular momentum provided by Chrysalis orbiting around Saturn. When Chrysalis was destroyed, Saturn lost this resonance, which could explain both the ring formation and the tilt mystery simultaneously. Computer simulations by the MIT team showed that out of 390 scenarios tested, 17 resulted in Chrysalis being destroyed in a way consistent with forming Saturn's current ring system. Suggesting this outcome, while not inevitable, is plausible given the right initial conditions. Yet another formation scenario proposes that a comet or large asteroid passed too close to Saturn and was torn apart by tidal forces. Comets, being loosely bound collections of ice and rock, are particularly vulnerable to tidal disruption. A comet on a trajectory that brought it within Saturn's Roche limit would be stretched by differential gravitational forces until it broke apart. The fragments would then spread into orbit, potentially forming rings. This scenario has the advantage of simplicity and doesn't require the destruction of any of Saturn's existing moons. However, it has difficulty explaining why Saturn's rings are so massive and so pure in composition. Comets typically contain significant amounts of rocky material and organic compounds, which should make the rings darker than they are. There's also an older hypothesis proposed by Robin Canup, a planetary scientist at the Southwest Research Institute. This scenario suggests that during Saturn's early history, when the planet was still surrounded by a gaseous nebula, a Titan-sized moon spiraled inward towards Saturn. Tidal forces stripped away the moon's icy mantle, scattering it into rings, while the rocky core continued falling into Saturn and was eventually absorbed by the planet. The initial rings in this scenario would have been far more massive than today's rings, perhaps 1,000 times more massive. Over time, material in the outer portions of these primordial rings would have coalesced to form some of Saturn's current inner moons, like Mimas, Enceladus, and Tethys. This would explain why these moons are primarily icy with relatively little rock. They formed from ring material that was already ice-rich. Regardless of which scenario is correct, and scientists continue to debate the details, all formation hypotheses share common features. First, violence. The rings didn't form peacefully from leftover material gently coalescing. They formed from destruction, from the catastrophic breakup of substantial bodies. Second, youth. The formation event occurred recently in cosmic terms within the last few 100 million years at most. Third, fortune. Humanity evolved at precisely the right time to witness Saturn's rings. If we had emerged a few 100 million years earlier, we would have seen a ringless Saturn. If we emerge a few 100 million years from now, assuming we survive that long, our descendants will again see a ringless Saturn. We live in a special moment in the planet's history, a fleeting window where the rings exist in all their glory. Ring dynamics, the gravitational ballet. Understanding Saturn's rings isn't just about knowing what they're made of or how they formed. It's about understanding the incredible dynamical processes that structure them, shape them, and ultimately doom them. The rings aren't static. They're in constant motion, governed by gravity, collisions, electrostatic forces, and interactions with Saturn's numerous moons. These processes create some of the most beautiful and complex structures in the solar system. Let's start with the shepherd moons. These are small moons that orbit within or very near the rings, using their gravity to sculpt the ring material. The most famous shepherd moons are Prometheus and Pandora, which maintain Saturn's F-ring. Prometheus orbits just inside the F-ring, while Pandora orbits just outside it. The gravitational influence of these two moons constrains the F-ring particles, preventing them from spreading outward or inward. Here's how it works. When ring particles drift too far outward, Pandora's gravity pulls them back inward. When particles drift too far inward, Prometheus's gravity nudges them back outward. The net effect is that the F-ring stays confined between these two shepherds, maintaining a narrow structure that would otherwise spread out over time due to collisions between ring particles. But the shepherding isn't perfect. As Prometheus orbits faster than the F-ring particles, being closer to Saturn, it periodically overtakes sections of the ring. Each time this happens, Prometheus gravitationally grabs ring material, creating channels and streamers in the ring. These perturbations create the braided appearance of the F-ring, making it look like multiple strands woven together. Cassini observed these structures in exquisite detail, watching them form, evolve, and dissipate over the course of hours and days. Pan and Daphnis are embedded moons that orbit within gaps in the ring. Pan maintains the Encke gap, while Daphnis maintains the Keeler gap. These moons are small. Pan is only about 16 miles across, while Daphnis is merely 4 miles in diameter, but their gravitational influence is sufficient to clear paths through the ring material. As they orbit, they push ring particles away from their immediate vicinity. Particles that drift too close to the moon are either gravitationally ejected from the gap or collide with the moon itself. The process isn't perfectly clean. High-resolution images show that Pan and Daphnis raise small waves in the ring material at the edges of their gaps, creating patterns that look like ripples spreading from a stone dropped in water. Gravitational resonances with larger, more distant moons create even more structure in the rings. A resonance occurs when ring particles orbit at periods that are simple integer ratios of a moon's orbital period. For example, particles in the Cassini division orbit twice for every one orbit of Mimas, Saturn's innermost major moon. This is called a 2-to-1 resonance. Every time Mimas completes one orbit, the ring particles at that location complete 2 orbits and find themselves in the same alignment with Mimas. This repeated gravitational tug, always in the same direction in space, gradually pumps up the eccentricity of the particles' orbits until they're ejected from the region. Over time, this clears out the Cassini division. It's not completely empty, as Voyager discovered, but the particle density is much lower than in the A and B rings. Other resonances create density waves rather than gaps. These are regions where ring particle density oscillates in spiral patterns, like grooves on a phonograph record. The particles aren't moving radially inward or outward. Instead, their orbits become slightly more elliptical and aligned with each other, creating regions of higher and lower density that spiral outward from the resonance location. Cassini measured many of these density waves and used them to determine properties of the rings, including the surface mass density and the speed of sound in the ring material. Yes, you read that correctly. Sound waves can propagate through Saturn's rings because the rings are dense enough that collisions between particles can transmit pressure waves. Bending waves are similar to density waves, but involve vertical motions rather than radial ones. When a moon's orbit is inclined relative to the ring plane, it can excite vertical oscillations in the rings at certain resonance locations. These create corrugations in the ring plane, regions where the ring thickness varies in a spiral pattern. Cassini observed dramatic bending waves, some creating vertical structures over 2 kilometers tall in regions of the rings. These towering structures cast long shadows when sunlight hits the rings at low angles, particularly during Saturn's equinox. The propeller features discovered by Cassini are another fascinating structure. These are patterns in the ring that look like airplane propellers, hence the name. Each propeller is created by a small moonlet, perhaps a few hundred meters in diameter, orbiting within the ring. The moonlet is too small to clear a complete gap like Pan or Daphnis does. Instead, it creates a partial clearing in its immediate vicinity, pushing ring material slightly outward and inward on either side of it. When viewed from above, this creates a propeller-shaped pattern with 2 lobes of reduced density flanking the central moonlet. Cassini discovered thousands of these propeller features in the ring, providing evidence that the ring contains numerous embedded moonlets that are too small to detect directly but reveal themselves through their gravitational influence on the surrounding particles. All of these structures exist in a delicate balance. The rings are incredibly thin. Most of the main rings are only 10 to 30 meters thick, despite spanning hundreds of thousands of kilometers in diameter. This extreme flatness is maintained by collisions between ring particles. When particles collide, they exchange momentum in ways that dampen vertical motions. Over time, collisions smooth the ring into a paper-thin disk aligned with Saturn's equatorial plane. If you could somehow take all the ring material and compress it into a single solid object, you could make a moon about 400 kilometers in diameter, slightly smaller than my mass. But spread out into a disk, that material creates one of the most spectacular sights in the solar system. The spokes, ghosts in the machine. Among all the strange phenomena in Saturn's rings, few are more mysterious than the spokes. These are radial features that appear in the B ring, looking like dark streaks extending from the inner edge of the ring outward toward the outer edge. Spokes were first discovered by Voyager 1 and 2 during their flybys of Saturn in 1980 and 1981. The discovery was completely unexpected. Nothing in ring dynamics theory predicted that such structures should exist. Here's why spokes are so strange. Ring particles orbit Saturn according to Kepler's laws of planetary motion. Particles closer to Saturn orbit faster than particles farther out. Any feature aligned radially, like the spoke of a wheel, should quickly shear apart as the inner particles race ahead of the outer particles. Within 1 or 2 orbits, a radial feature should transform into a spiral and then dissolve completely. Yet the spokes maintain their radial orientation for hours, rotating with the rings as if they were solid structures painted onto the ring surface. The leading explanation involves electrostatics and Saturn's magnetic field. Here's the proposed mechanism. Tiny dust particles in the rings, particularly particles measuring micrometers to tens of micrometers in size, can become electrically charged through various processes. Ultraviolet light from the sun can knock electrons off the particles' surfaces, giving them a positive charge. Impacts from high-energy plasma particles in Saturn's magnetosphere can also charge the particles. Once charged, these tiny particles respond to Saturn's magnetic field in addition to Saturn's gravity. Saturn's magnetic field rotates with the planet every 10.7 hours, which is much faster than the ring's orbit. The field is approximately aligned with Saturn's rotation axis, meaning field lines emerge from the planet, arc out into space, and return to the planet at different longitudes. When charged ring particles interact with these field lines, they can be levitated slightly above the main ring plane. Because they're no longer embedded in the dense ring material, they don't collide with other particles as frequently. They can maintain their radial alignment because they're being guided by the magnetic field rather than purely by orbital mechanics. The spokes appear dark when viewed with the sun behind the observer, backlit geometry, but bright when viewed with the sun in front of the observer, forward scattered light. This behavior is consistent with small particles. Microscopic dust scatters light differently than larger particles or chunks of ice. In backscattered light, small particles absorb more light than they reflect, appearing dark. In forward scattered light, they scatter sunlight around themselves, appearing bright. This optical behavior confirms that spokes consist of very fine dust, much smaller than the typical ring particles. Spokes are a seasonal phenomenon. They're most prominent when Saturn is near its equinox, the times when the Sun crosses Saturn's equatorial plane. During these periods, sunlight hits the rings nearly edge-on, creating conditions that may enhance the charging processes that create spokes. Spokes largely disappeared from view during Cassini's early years at Saturn, when the planet was in its southern summer and the Sun was tilted well above the ring plane. But as Saturn approached its equinox in 2009, spokes began reappearing, confirming their seasonal nature. There's also evidence linking spokes to Saturn's powerful radio emissions, called Saturn kilometric radiation. Carolyn Porco, the imaging team leader for both Voyager and Cassini, discovered in the 1980s that spoke activity correlated with bursts of this radio emission. Both phenomena varied with a period matching the rotation of Saturn's magnetic field. This suggests that spokes are indeed connected to electromagnetic processes in Saturn's magnetosphere. Despite decades of study, many questions about spokes remain unanswered. What initially lifts the dust particles above the ring plane? Some theories suggest micrometeoroid impacts onto the rings eject dust that then becomes charged and levitated. Others propose that instabilities in Saturn's magnetic field create electric fields strong enough to lift charged dust directly. How high do the spokes extend above the ring plane? Measurements suggest heights of tens to hundreds of kilometers, but precise values are difficult to obtain. Why do spokes appear in the B ring but not prominently in other rings? This might relate to the B ring's particular optical depth and particle size distribution, but the details remain unclear. Spokes serve as a reminder that Saturn's rings aren't just a passive disk of ice and rock governed solely by gravity. They're an active, dynamic system where electromagnetic forces, plasma physics, and dust dynamics all play roles. The rings interact with Saturn's magnetosphere, with the solar wind, and with the stream of interplanetary dust flowing through the solar system. They're far more complex than early astronomers, seeing them as simple bands through their telescopes, could ever have imagined. The ugly truth: Saturn is eating its rings. Now we arrive at the heart of the matter. The ugly truth that gives this video its title. Saturn is consuming its own rings. Right now, as you watch this, Saturn's rings are raining down onto the planet. 22,000 pounds of ring material per second is falling from the rings into Saturn's atmosphere. That's not a typo. Every single second, 10 tons of water ice vanishes from the rings and plunges into the gas giant below. Every hour, 36,000 tons. Every day, 864,000 tons. Every year, 315 million tons of ring material disappears forever. At that rate, the rings won't last. Scientists estimate that if the current loss rate continues, Saturn's magnificent rings will be gone in about 100 million to 300 million years. That might sound like a long time, and by human standards it is, but in the lifespan of the solar system, it's the blink of an eye. Saturn has existed for 4.5 billion years. The rings, as we've discussed, are probably only 10 million to 100 million years old. They'll be gone in another 100 million to 300 million years. That means the rings exist for only about 1 to 10% of Saturn's total lifetime. They're a temporary phenomenon, a fleeting moment in planetary history. The process causing this loss is called ring rain, and Cassini provided the first direct measurements of it during the grand finale orbits. Here's how it works. Ring particles, particularly the smaller ones, are constantly colliding with each other. These collisions create fine dust. Additionally, ultraviolet light from the Sun and charged particles in Saturn's magnetosphere constantly bombard the ring particles, knocking atoms and molecules off their surfaces. These processes create a cloud of microscopic ice grains and water molecules surrounding the rings. Saturn's magnetic field plays a crucial role in what happens next. The magnetic field lines emerge from Saturn's north magnetic pole, arc out into space, and re-enter at the south magnetic pole. These field lines pass through the ring plane, and they're not static. The magnetic field rotates with Saturn, completing one rotation every 10.7 hours. Water molecules and ice grains in the vicinity of the rings can become ionized, meaning they acquire an electric charge. Once charged, these particles interact with Saturn's magnetic field. They become trapped on magnetic field lines and are dragged along as the field rotates. But here's the key. The magnetic field lines don't remain at the same distance from Saturn as they pass through the ring plane. They connect to Saturn's ionosphere, the outer layers of the planet's atmosphere. Charged particles following these field lines spiral down towards Saturn, pulled by the planet's gravity and guided by the magnetic field. As they fall, they accelerate, reaching speeds of thousands of kilometers per hour. When they reach Saturn's upper atmosphere, they collide with atmospheric molecules, depositing their mass and energy into the planet. The ring rain creates a visible effect on Saturn. Observations by ground-based telescopes in the 1980s and 90s detected excess hydrogen emission from specific latitudes in Saturn's upper atmosphere. These latitudes correspond to the regions where magnetic field lines that pass through the rings connect to Saturn's atmosphere. The emission comes from ring material vaporizing as it slams into the atmosphere at high velocity. The water molecules break apart in the heat of atmospheric entry, releasing hydrogen that glows in specific wavelengths of light. The Cassini spacecraft measured this process directly during its grand finale dives. As Cassini passed between Saturn and the rings, it flew through the region where ring rain falls toward the planet. The spacecraft's instruments detected charged water molecules and water ice grains streaming down towards Saturn. By measuring the density and velocity of this material, scientists calculated the mass loss rate, 22,000 pounds per second, or roughly 10 metric tons per second. This number shocked many researchers. Previous estimates of ring loss rates, based on modeling and indirect observations, had suggested much lower values. Some models predicted the rings might last 1 billion years or more. The direct Cassini measurements revealed that the rings are disappearing much faster than anyone expected. Combined with the low total mass of the rings, this rapid loss rate means the rings are living on borrowed time. There's another loss mechanism as well, one that affects the outermost regions of the ring system. Meteoroid bombardment constantly strikes the rings, kicking particles into different orbits. Some of these particles gain enough velocity to escape the ring system entirely. Others are knocked into higher orbits where they're more exposed to drag from Saturn's extended atmosphere and the pressure of sunlight. Over time, these effects erode the outer edges of the ring system. The ring rain isn't uniform across the rings. The loss rate is highest in regions where the rings are densest and where the magnetic field lines make the best connection between the rings and Saturn's ionosphere. The B ring, being the most massive ring, contributes significantly to the ring rain. The C ring, being closer to Saturn, also loses material rapidly. The ring loses material as well, though perhaps at a slightly lower rate due to its greater distance from Saturn. What's particularly sobering is that this process is irreversible. There's no mechanism replenishing the main rings. The E ring is continuously replenished by Enceladus's geysers, but the main rings, the A, B, and C rings that create Saturn's iconic appearance, have no such source. They're shrinking, eroding, disappearing grain by grain and ton by ton into the planet they orbit. Every second that passes, the rings become slightly less massive. Every year that goes by, they become slightly less bright. Over millions of years, they will fade from spectacular to modest to barely visible and finally to non-existent. Some scientists have suggested that perhaps the rings undergo cycles. Maybe they form, get consumed, then reform from new material, but there's no evidence for such cycles and no clear mechanism to create them. The destruction of a moon is not a regular, repeating event. It's a random catastrophe. If Saturn's rings formed from a moon collision or tidal disruption, that was a one-time event, not part of a cycle. When these rings are gone, they're gone for good. The implication is profound. We live in a cosmically special time. If humans had evolved a few 100 million years earlier, we would look up at Saturn through our telescopes and see a planet without rings, or perhaps with only very faint, thin rings like Jupiter has. If our descendants survive for a few 100 million years into the future, they will look at Saturn and see a planet whose rings have faded to shadows of their former glory or vanished completely. Right now, in this brief window of cosmic history, Saturn has magnificent rings. We are here to see them. That's not just fortunate, it's almost miraculous. This realization has changed how planetary scientists think about ring systems. Jupiter has rings, but they're faint and composed primarily of dust knocked off the planet's small inner moons. Uranus and Neptune have rings, but they're dark, narrow, and far less impressive than Saturn's. For years, scientists wondered why Saturn alone had such spectacular rings. The answer, it seems, is luck and timing. Saturn doesn't have special properties that create permanent rings. It just happens to have experienced a moon-destroying event within the last 100 million years, creating a spectacular but temporary ring system. Jupiter, Uranus, and Neptune may have had spectacular rings in their past. They might have them again in the future if the right catastrophe occurs. But right now, Saturn is the only gas giant with a truly magnificent ring system, and that won't last. Cassini's grand finale, the mission that changed everything. To understand how we know all this, we need to talk about the Cassini mission, one of the most successful planetary exploration missions in history. Cassini launched in October 1997 a joint mission between NASA, the European Space Agency, and the Italian Space Agency. The spacecraft was massive, weighing nearly 6 tons, and carried 12 scientific instruments designed to study Saturn, its rings, its magnetosphere, and its moons. Attached to Cassini was the Huygens probe, built by the European Space Agency, designed to land on Saturn's largest moon, Titan. Cassini arrived at Saturn on June 30, 2004, executing a flawless orbit insertion burn that slowed the spacecraft enough to be captured by Saturn's gravity. For the next 13 years, Cassini orbited Saturn, revolutionizing our understanding of the Saturnian system. The mission discovered new moons, observed weather patterns on Saturn, measured the structure of the rings in unprecedented detail, and made groundbreaking discoveries about Saturn's moons. The most famous discovery was probably the geysers on Enceladus. In 2005, Cassini flew close to this small icy moon and discovered enormous plumes of water vapor and ice particles erupting from fractures near the South Pole. These geysers showed that Enceladus has a subsurface ocean of liquid water, making it one of the most promising places in the solar system to search for extraterrestrial life. Cassini flew through the plumes multiple times, sampling their composition and discovering organic molecules, salts, and other compounds that suggested the ocean beneath Enceladus's ice is in contact with a rocky seafloor, creating conditions that might support life. Cassini also discovered that Titan, Saturn's largest moon, has a complex methane cycle analogous to Earth's water cycle. Titan has clouds, rain, rivers, lakes, and seas, all made of liquid methane and ethane rather than water. The Huygens probe landed on Titan's surface in January 2005, returning the only images we have of the surface of a body in the outer solar system. The landscape showed rounded rocks of water ice, carved by flowing methane, sitting on a surface that had the consistency of wet sand. Cassini's ring observations were equally revolutionary. The spacecraft observed the rings continuously for 13 years, watching them evolve through nearly half of Saturn's seasonal cycle. Cassini observed the rings at all angles, from edge-on during Saturn's equinox in 2009 to fully open during the southern summer. The spacecraft captured images of the rings at resolutions as fine as a few meters per pixel, revealing details that ground-based telescopes could never see. Cassini discovered propeller features, monitored the evolution of the braided F-ring, watched as Pan and Daphnis raised waves in the surrounding ring material, observed density waves and bending waves, tracked the seasonal appearance and disappearance of spokes, and discovered new small moons embedded within the rings. Each observation added to our understanding of ring dynamics. But the most important ring observations came during Cassini's final year, the grand finale. By 2017, Cassini was running low on propellant. The mission team faced a choice. They could let the spacecraft drift into an uncontrolled orbit that might eventually crash into one of Saturn's moons, potentially contaminating them with terrestrial microbes that might have survived on the spacecraft, or they could deliberately destroy Cassini in Saturn's atmosphere, ensuring it could never contaminate the moons. They chose the latter, but not before designing one last series of daring observations. The grand finale orbits took Cassini where no spacecraft had ever gone, between Saturn and its rings. Starting in April 2017, Cassini executed 22 orbits that brought it within about 2,000 kilometers of Saturn's cloud tops and just inside the D-ring, the innermost ring. These orbits were dangerous. Nobody knew for certain how much dust existed in the gap between Saturn and the rings. Even tiny particles at orbital velocities could damage or destroy the spacecraft. To protect itself, Cassini oriented its large dish antenna toward the direction of motion during each pass, using it as a shield. Orbits succeeded brilliantly. The gap between Saturn and the rings turned out to be surprisingly clear, containing less dust than feared. This allowed Cassini to make unprecedented measurements of Saturn's gravitational field and magnetic field. By tracking the spacecraft's position with incredible precision using radio signals sent to Earth, scientists measured how Saturn's gravity pulled on Cassini. These measurements revealed the distribution of mass inside Saturn with unprecedented accuracy. More importantly for our story, the measurements allowed scientists to determine the mass of the rings. Here's how it worked. Saturn's gravity includes contributions from both the planet and the rings. When Cassini was far from the rings, it felt only Saturn's gravity. But during the grand finale orbits, when Cassini passed very close to the rings, it felt the gravitational pull of the ring material as well. By comparing the spacecraft's trajectory during these close passes to models of Saturn's gravity, scientists could calculate how much mass the rings contained. The result was definitive. The rings contain about 15 million billion tons of material, or roughly 40% the mass of Saturn's moon Mimas. This was significantly less than many previous estimates, combined with observations of how clean and bright the rings are. This low mass strongly suggested that the rings are young, probably less than 100 million years old. During the grand finale orbits, Cassini also flew through the region where ring rain falls into Saturn. The spacecraft's instruments detected charged water molecules and ice grains streaming down the magnetic field lines towards Saturn's atmosphere. The radio and plasma wave science instrument measured the density of charged particles. The cosmic dust analyzer detected ice grains. The iron and neutral mass spectrometer measured the composition of the material. Together, these measurements provided the first direct confirmation of ring rain and the first accurate measurement of the mass loss rate. On September 15, 2017, Cassini executed its final maneuver. The spacecraft dove into Saturn's atmosphere, transmitting data until the very end. As it plunged deeper, the atmosphere grew denser, eventually tearing the spacecraft apart. Cassini burned up in Saturn's atmosphere, becoming part of the planet it had studied for 13 years. The mission team chose this fate deliberately, ensuring that Cassini could never contaminate Enceladus or Titan with terrestrial microbes. But in those final moments, Cassini sent back unprecedented data about Saturn's atmosphere, completing its mission to the very end. The legacy of Cassini is immense. The mission returned over 450,000 images. It discovered 7 new moons. It revealed Enceladus as a potentially habitable world. It showed us Titan's alien landscapes, and it revolutionized our understanding of Saturn's rings, revealing them to be young, dynamic, and temporary. Without Cassini, we would still believe the rings were ancient, primordial features of the solar system. Thanks to Cassini, we now know the truth. The rings are recent, violent creations destined to disappear within a few 100 million years. The 2025 Edge-On event, when the rings vanish. In March 2025, something remarkable will happen. Saturn's rings will vanish. From Earth's perspective, the rings will become essentially invisible, appearing as nothing more than a thin line crossing Saturn's disk. This isn't a new phenomenon. It happens every 13 to 16 years and has been observed throughout the history of telescopic astronomy. But it's worth understanding why it happens and what it tells us about the rings. Saturn's axis is tilted at about 27 degrees relative to its orbital plane, just as Earth's axis is tilted at 23.5 degrees. This tilt means that as Saturn orbits the Sun, which takes 29.5 Earth years, we see the rings from different angles. For about half of Saturn's orbit, we see the rings tilted toward us from the north. For the other half, we see them tilted toward us from the south. Twice per orbit, we see the rings exactly edge-on. The rings are incredibly thin. While they span over 270,000 kilometers in diameter, they're only about 10 meters thick in most places, and at most around 30 meters thick, even in the densest regions. If you scaled Saturn down to the size of a basketball, the rings would be thinner than a sheet of paper. When viewed edge-on, something that thin simply disappears from view, even through powerful telescopes. The rings don't reflect enough light when seen edge-on to be visible from Earth. The upcoming edge-on viewing in March 2025 will be the first such event since 2009. The exact ring plane crossing will occur on March 23, 2025. During the 2009 event, the Cassini spacecraft was orbiting Saturn and captured stunning images of the rings, illuminated by sunlight shining exactly along the ring plane. These images revealed vertical structures in the rings that are normally impossible to see. When sunlight hits the rings at a grazing angle, even small vertical variations cast long shadows, making features like bending waves and warps dramatically visible. From Earth in 2025, amateur astronomers and professional observatories would normally watch as Saturn's rings gradually tilt toward edge-on orientation and then vanish. However, this particular event will be challenging to observe. Saturn will pass through conjunction with the Sun on March 12, 2025, placing it very close to the Sun in Earth's sky during the actual ring plane crossing on March 23. This proximity to the Sun means the glare will make observation extremely difficult or impossible for most viewers. The planet won't emerge from the Sun's glare until late April, when it will appear in the pre-dawn sky. The edge-on viewing lasts only a short time. Saturn is moving in its orbit, and Earth is moving in its orbit, so the viewing geometry changes relatively quickly. The rings will appear nearly edge-on again in November 2025, specifically around November 23, when they'll be at their narrowest from Earth's perspective during this apparition. This November viewing will be much more favorable for observation since Saturn will be farther from the Sun in the sky. After that date, the rings will finally start the slow transition to wide visibility again. By 2032, the rings will reach their maximum tilt as seen from Earth, displaying the southern face of the rings at peak visibility. For the best view of a true ring plane crossing that's also well placed for observation, skywatchers will have to wait until 2038 and 2039, which will feature 3 ring plane crossings under much better viewing conditions. These edge-on events have historical significance. They caused Galileo's confusion when Saturn's companions vanished in 1612. They allow astronomers to search for small moons that orbit close to the rings, which are normally lost in the ring's glare. The 2009 edge-on event led to the discovery of several new moons and moonlets embedded within or near the rings. The 2025 event will provide another opportunity to search for these objects. Edge-on events also allow measurements of the ring's thickness with great precision. By observing how long the rings take to disappear and reappear, and by measuring the brightness of the rings during the crossing, astronomers can calculate the vertical extent of the ring material. These measurements confirm that the main rings are extremely flat, while also revealing that some features, like the F ring, have greater vertical structure. After 2025, the next edge-on viewing won't occur until around 2038 or 2039, depending on the exact orbital alignments. These events are rare from any given person's perspective. If you were born in 2010, you were too young to remember the 2009 event. The 2025 event, while technically occurring, won't be easily observable due to Saturn's proximity to the Sun. The November 2025 near edge-on viewing will offer a better opportunity. For anyone hoping to see a well-placed, easily observable ring plane crossing, 2038 will be the next prime opportunity. For anyone over about 40 years old in 2025, the 2009 event may have been their last easily observable ring plane crossing, making the 2038 event particularly special when it arrives. This rarity makes the event special. It's a reminder that astronomy isn't just about looking at static objects in the sky. The heavens are dynamic, constantly changing as planets orbit, moons revolve, and viewing geometries evolve. Saturn's rings are always there, always orbiting the planet, but whether we can see them depends on our perspective. The 2025 event will remind everyone watching that perspective matters, that the universe looks different from different vantage points, and that timing determines what we can observe. Broader implications, what this means for planetary science. The discoveries about Saturn's rings have implications that extend far beyond Saturn itself. They've changed how planetary scientists think about ring systems throughout the universe and how we understand the long-term evolution of planetary systems. First, the realization that Saturn's rings are young and temporary means that ring systems in general are probably transient features. For decades, astronomers assumed that if a gas giant had rings, it probably always had rings and would continue to have rings indefinitely. Saturn's case shows that assumption was wrong. Ring systems can form suddenly from catastrophic events and then disappear over geologically short timescales. This means that at any given moment, most gas giants in the universe probably don't have prominent ring systems. Saturn is unusual not because it has special properties that create permanent rings, but because we're observing it during a brief window when it happens to have rings. This realization affects how we interpret observations of exoplanets, planets orbiting other stars. Astronomers have discovered thousands of exoplanets, including many gas giants. Some of these planets might have ring systems, but detecting rings around exoplanets is extraordinarily difficult with current technology. If ring systems are temporary, then even if we could survey every gas giant in the galaxy, only a small fraction would have prominent rings at any given time. Saturn's rings aren't the default state for gas giants. They're an exception, a special case. Second, the discovery of ring rain and the rapid loss of ring material has implications for how rings interact with the planets they orbit. Material falling from rings into a planet's atmosphere deposits mass and energy. For Saturn, 10 tons per second might sound like a lot, but compared to Saturn's total mass of 568 billion trillion tons, it's negligible. Saturn won't gain significant mass from consuming its rings. But the energy deposited in Saturn's upper atmosphere might affect atmospheric chemistry and dynamics in subtle ways. The excess hydrogen emission detected at specific latitudes is direct evidence of this interaction. For smaller planets, ring rain might have more significant effects. If a planet the size of Neptune or Uranus had a massive ring system that was rapidly decaying, the influx of material into the atmosphere could potentially affect the planet's observable properties. Some scientists have speculated that observed anomalies in the atmospheres of some exoplanets might be explained by ring systems that are currently decaying and dumping material into the planet. Third, the moon collision scenario for ring formation raises questions about how common such events are. In our solar system, we have 4 gas giants: Jupiter, Saturn, Uranus, and Neptune. All 4 have rings, but only Saturn's are prominent. Jupiter's rings are faint and dusty, continuously replenished by material knocked off small moons by meteoroid impacts. Uranus has narrow, dark rings, possibly the remnants of a much more massive ring system that has mostly been lost. Neptune has incomplete ring arcs, confined by shepherd moons. None of these ring systems rivals Saturn's in brightness, mass, or visual impact. This suggests that moon-destroying events might be rare. If they were common, we might expect to see multiple gas giants with prominent ring systems at any given time. The fact that only Saturn has truly spectacular rings suggests that the events creating such rings happen infrequently, perhaps once every few billion years per planet. Saturn got lucky recently. Jupiter, Uranus, and Neptune either haven't experienced such an event recently or lost their rings to decay long ago. The dynamics of moon collisions and tidal disruptions depend on many factors. The spacing of moons in a planetary system matters. If moons are widely separated, resonances are less likely to drive orbits unstable. The tidal forces exerted by the sun matter. The presence of other large moons that can perturb orbits matters. The Roche limit's location, which depends on the planet's mass and density, matters. All of these factors combine to make moon-destroying events probabilistic rather than inevitable. Some planetary systems will experience them, others won't. Fourth, the young age of Saturn's rings connects to broader questions about the age and evolution of Saturn's moon system. Several of Saturn's moons are small, icy, and have relatively smooth surfaces, suggesting they're geologically young. Enceladus, with its active geysers, is clearly a young, dynamic world. The chrysalis hypothesis suggests that Saturn's entire inner moon system might be younger than previously thought, perhaps forming from ring material that coalesced outside the Roche limit over the past few 100 million years. This challenges earlier assumptions that Saturn's moons formed billions of years ago during the planet's formation. If moons can form recently from ring material, and if ring material comes from destroyed moons, then the moon system is not static. It evolves. Moons form, survive for a time, get destroyed, form rings, and the rings eventually either fall into Saturn or coalesce into new moons outside the Roche limit. This cycle might have repeated multiple times over Saturn's history. The moons we see today might not be the same moons that orbited Saturn a billion years ago. Finally, the discoveries about Saturn's rings remind us how much there is still to learn. Despite 13 years of Cassini observations, many questions remain unanswered. We still don't know exactly when the rings formed. We don't know which formation scenario is correct. We don't fully understand the spoke phenomenon. We don't know how long each individual particle survives in the rings before being destroyed by collisions or ejected by moonlit impacts. We don't know whether the ring loss rate is constant or varies over time. We don't know whether Saturn had earlier ring systems that formed and decayed before the current rings appeared. These unknowns drive the case for future missions to Saturn. NASA and ESA are considering several mission concepts, including orbiters, atmospheric probes, and even small satellites that could fly through gaps in the rings to sample ring material directly. Each new mission would answer some questions while undoubtedly raising new ones. That's how science progresses, by replacing ignorance with knowledge and vague questions with precise ones. The lucky timing of human existence. Let's step back and appreciate just how fortunate we are. Modern humans, Homo sapiens, evolved roughly 300,000 years ago in Africa. For the vast majority of our existence, we had no idea Saturn existed. The planet is visible to the naked eye, and ancient cultures certainly observed it, but they had no concept that it was a world, that it had rings, or that it was anything other than a wandering star moving against the fixed background of the heavens. Galileo turned his telescope towards Saturn in 1610, less than 415 years ago. That's when humanity first glimpsed the rings. Though we didn't understand what we were seeing. Only in 1655, 370 years ago, did Huygens correctly identify them as a ring system. For 370 years, a tiny fraction of human existence and an infinitesimal fraction of human evolutionary history, we've known that Saturn has rings. Now consider the timeline of the rings themselves. They formed, at most, 100 million years ago, and more likely within the last 10 million to 50 million years. They'll disappear in 100 million to 300 million years. The total lifespan of Saturn's current ring system is perhaps 400 million years at maximum, probably less. Saturn itself is 4.5 billion years old and will continue to exist for billions more years until the Sun becomes a red giant and incinerates the inner solar system. Do the math. The rings exist for less than 10% of Saturn's total lifetime, probably less than 5%. And humanity, specifically modern humans with the technology to observe the rings, exists during that brief window. We weren't around for the billions of years before the rings formed. We probably won't be around for the billions of years after they disappear. We are here now, at precisely the right time to see Saturn with its magnificent rings. Some people might call this coincidence. Some might invoke the anthropic principle, suggesting that we shouldn't be surprised to find ourselves in a universe where we can observe interesting phenomena, because if the universe weren't interesting, we wouldn't be here to observe it. But even within that framework, the timing is remarkable. There's nothing about the existence of intelligent life that requires Saturn to have rings. Humanity could have evolved in a solar system where Saturn was ringless, and we'd never know what we were missing. This timing has philosophical implications. It reminds us that the universe we observe is not static and unchanging. The cosmos today looks different than it did a billion years ago and will look different again a billion years from now. Stars are born and die. Galaxies merge. Planetary systems evolve. We're not observing a frozen tableau. We're witnessing a single frame in a cosmic film that has been playing for nearly 14 billion years and will continue for trillions more. It also reminds us that exploration is time-sensitive. If humanity delays too long in exploring the solar system, some opportunities will be lost forever. In a few 100 million years, assuming humans or our descendants still exist, there will be no spectacular rings to study. Future scientists will have to rely on whatever data we collect now to understand what Saturn's rings were like. They'll look at our images, read our papers, and perhaps wish they could have seen the rings firsthand. This lends urgency to planetary exploration. Every mission we fly, every observation we make, is collecting data about the solar system as it exists now. That data will be valuable not just for answering current scientific questions, but for providing a historical record for future generations. The images Cassini returned aren't just pretty pictures. They're a snapshot of Saturn's ring system at this particular moment in its evolution. Centuries or millennia from now, when the rings have faded, those images will be irreplaceable historical documents. The lucky timing also applies to individual humans. If you're alive today, you have the opportunity to see Saturn's rings through a telescope or in images returned by spacecraft. That opportunity didn't exist for the roughly 100 billion humans who lived and died before Galileo invented the telescope. It might not exist for humans living hundreds of millions of years in the future, assuming our species survives that long. You're living in the narrow window where both Saturn has rings and humanity has the technology to observe them. That's worth pausing to appreciate. What happens when the rings are gone? Let's project forward and imagine what Saturn will be like after its rings have vanished. The process will be gradual. Over millions of years, the rings will slowly fade as material continues to rain down into Saturn's atmosphere. The B ring, being the most massive, will probably survive the longest. The C and D rings, being closer to Saturn, will likely disappear first. The ring will fade away at a rate somewhere between the two. Eventually, perhaps 100 million years from now, perhaps 300 million years from now, the last traces of the main rings will vanish. What will remain? Probably something similar to Jupiter's ring system. Jupiter has a faint, thin ring composed primarily of dust. This ring is constantly replenished by material knocked off Jupiter's small inner moons, Metis, Adrastea, Amalthea, and Thebe, by meteoroid impacts. As long as these moons exist and continue to be bombarded, Jupiter's ring will persist, though it's so faint that it wasn't discovered until Voyager 1 photographed it in 1979. Saturn has similar small inner moons that could sustain a faint dust ring. Pan, Daphnis, Prometheus, Pandora, and other moonlets embedded in or near the current rings will continue to orbit Saturn long after the main rings are gone. Meteoroid impacts on these moons will eject dust that spreads into orbit. This dust will form a tenuous ring, perhaps visible to spacecraft but invisible from Earth. The E ring will likely persist because it has an active source, Enceladus's geysers. As long as Enceladus remains geologically active, it will continue pumping water vapor and ice particles into space, replenishing the E ring. However, Enceladus's activity depends on tidal heating, which in turn depends on the orbital resonance between Enceladus and Dione. If that resonance is lost, perhaps due to tidal evolution changing the moon's orbits, Enceladus will freeze, the geysers will stop, and the E ring will fade within a few centuries as its particles fall into Saturn or are swept away by radiation pressure. Saturn itself will continue to exist much as before. The planet's appearance, as seen from Earth, will change dramatically. Without the rings, Saturn will appear as a yellowish sphere with faint bands, similar to Jupiter but smaller and less detailed. The planet will lose much of what makes it instantly recognizable. For centuries, Saturn has been the ringed planet, the jewel of the solar system. Without rings, it becomes just another gas giant. From close up, the changes will be more subtle. Saturn's magnificent cloud patterns, its storms, its hexagonal jet stream at the North Pole, and its aurorae at both poles will all remain. The planet's dozens of moons will continue orbiting. Titan will still have its thick atmosphere and methane lakes. Enceladus will still have geysers, at least for a while longer. Iapetus will still display its bizarre two-toned coloration. With one hemisphere bright and one hemisphere dark, the Saturnian system will remain scientifically fascinating even without rings. But something ineffable will be lost. The rings are beautiful, they're inspiring, they've captured human imagination for 4 centuries, they've appeared in countless works of science fiction, inspiring visions of exploration and wonder. A Saturn without rings will be a diminished Saturn, at least from an aesthetic perspective. There's a melancholy to this realization. The universe is not obligated to preserve beauty for our benefit. Natural wonders come and go on their own timescales, indifferent to whether anyone is watching. The rings existed for millions of years before humans evolved. They'll disappear long before the sun dies. They don't care whether we appreciate them. They're just following the laws of physics, raining slowly into Saturn in accordance with electromagnetic and gravitational forces. This melancholy extends to the broader cosmos. Everything is temporary. Stars burn out. Galaxies merge and eventually evaporate as their stars are flung into intergalactic space by gravitational interactions. On the longest timescales, even protons might decay, reducing all matter to radiation. The universe is not static. It's evolving, and that evolution is generally in the direction of increasing entropy, increasing disorder, and decreasing structure. But there's another way to look at it. The temporary nature of Saturn's rings makes them more precious, not less. If the rings were eternal, permanent fixtures of the solar system guaranteed to last forever, they'd be less special. It's precisely because they're fleeting, because we're witnessing them during a narrow window of time, that makes them remarkable. We're seeing something rare, something that won't last, something that future generations will know only through our observations and measurements. This perspective applies to all natural wonders, not just Saturn's rings. The Grand Canyon will eventually erode flat. Mount Everest will eventually be worn down to a plain. The sun will eventually expand and destroy Earth. Nothing lasts forever. The proper response isn't despair but appreciation. We are here now. We can see Saturn's rings now. That's enough. Conclusion: appreciating the fleeting cosmos. We've covered a lot of ground in this deep dive into Saturn's rings. We've traced the history of their discovery from Galileo's confusion to Cassini's comprehensive observations. We've examined their composition, structure, and dynamics, from the kilometer-sized chunks in the B ring to the microscopic dust-creating spokes. We've explored the violence of their formation, probably resulting from a catastrophic moon collision within the last 100 million years. We've understood the complexity of their dynamics, shaped by shepherd moons, gravitational resonances, and electromagnetic forces. We've witnessed the mystery of spokes, ghostly radial features that shouldn't exist according to simple orbital mechanics, but persist due to electromagnetic levitation of charged dust. Most importantly, we've confronted the ugly truth. Saturn's rings are dying. Right now, 10 tons of ring material per second is raining into Saturn's atmosphere, vanishing forever. At that rate, the rings will be gone in 100 million to 300 million years, a fleeting moment in the lifespan of the solar system. We humans exist at precisely the right cosmic moment to witness Saturn with its magnificent rings. A few 100 million years earlier or later, and we would have missed them entirely. The story of Saturn's rings is a story about time, perspective, and the transient nature of cosmic beauty. It's a reminder that the universe we observe today is not the universe of the past or the future. Everything changes, everything evolves. The rings that Galileo first glimpsed 400 years ago won't exist 400 million years from now. They're temporary, ephemeral, precious precisely because they won't last. This knowledge should change how we think about exploring the solar system. Every mission matters. Every observation counts. The data we are collecting now about Saturn's rings isn't just for answering current scientific questions. It's creating a historical record of what the rings were like at this particular moment in their existence. When the rings are gone, future scientists will rely on our measurements to understand what they once were. That's a profound responsibility. It should also inspire us to look up more often, to appreciate what's out there while it's still there. Saturn is visible to the naked eye as a bright yellowish point of light. Through even a small telescope, the rings are apparent, a sight that still inspires wonder 4 centuries after Galileo first saw them. Every clear night is an opportunity to witness something that won't last forever, something that exists now but won't exist for most of cosmic history. The ugly truth about Saturn's rings isn't really ugly at all. It's bittersweet. Yes, the rings are disappearing. Yes, they're temporary. Yes, we're witnessing their slow destruction in real time, but we're also incredibly fortunate to be here to see them. Out of the billions of years of Saturn's existence, we happen to live during the brief window when the rings are at their most spectacular. That's not ugly, that's miraculous. So the next time you see Saturn, whether through a telescope or in an image from a spacecraft, take a moment to appreciate what you're seeing. Those rings are ancient by human standards, but they're young by cosmic standards. They're massive, containing material equivalent to 2/3 of Antarctica's ice sheet, but they're disappearing ton by ton every second. They're beautiful, spectacular, inspiring, and they won't be there forever. The universe is full of wonders, and Saturn's rings are among the greatest. But they're temporary wonders, transient beauty in an ever-changing cosmos. We're witnessing them now. That's a gift, a stroke of cosmic luck, a reminder that sometimes being in the right place at the right time means being on a small blue planet, orbiting an average star, during the brief period when the sixth planet from that star happens to have the most magnificent ring system in the solar system. Appreciate it while it lasts, because like everything else in the universe, it won't last forever. If you found this deep dive into Saturn's rings fascinating, give this video a like and subscribe to the channel for more explorations of space science and cosmic discoveries. Hit the notification bell so you don't miss future videos about the wonders and mysteries of our universe. Thanks for watching, and keep looking up at the stars.